Hello, everyone. We're week 4, and what you've been waiting for, we are finally talking about transformers. So, yes, and we'll spend today's lecture, half of it on it, really going in depth, trying to give you the right intuitions so that we can build next week. We'll talk about the multimodal version, but today we'll just talk about those self-attention models. Just a few administrative things. Don't forget the deadline for the we have the deadline for the first project assignment. And as I mentioned, my Monday is now reserved for reading all of these so that we have meetings plans on Friday, on Wednesday and Friday, in fact. So I sent already this to Piazza. Each team are invited to sign up. It is not a requirement. If you know everything, you're all set, but it will be a pleasure to meet with each team. So I reserved about 7 hours of time so that I can meet each team for at least 15 minutes. And before that, I will have read. So write the research ideas as you can. Like, in the sense, try to make them as different as possible. If you put 1 or 2 extra ideas, it's not a problem. I mean, I don't go and write like 20 ideas. That doesn't help us. But like if you want 1 or 2 extra, that's okay. I will give you feedback, which one are manageable, how to improve, also maybe papers related to that. And we will be working over the next few weeks with the TAs also to finalize these ideas. There will be another round of meetings. Usually it's after the midterm. After the midterm, at that point, you should almost have a final draft of your research ideas. And that will be the second time where I'm planning to meet with all teams. Otherwise, meet often with your TA, primary TA. And if you have other questions, at the end of the lectures, usually is a good time to talk as well. So for many topics, Paul knows a lot more than me, or as much or more. So there's a lot of topics also where I will say, hey, why don't you also talk with Paul so that he can give you different guidelines as well. So it's a really nice plus all the TAs. Okay, so today we will talk about 2 things, aligned representations, and also I will finish the continuous alignment that I didn't have time to complete last lecture. So let's start with this idea of continuous alignment. Okay. Continuous alignment is because we talked earlier about discrete alignment in the sense that I have discrete elements. I like a list of objects and I have words and I'm aligning them. But for many cases, you work with a signal that doesn't have an obvious way of segmenting it. You have motion, also videos that don't always have that clear way of segmenting. So then the alignment, because even the definition of an element may not be completely clear. These are the interesting part. And I think there's still a lot more research to be done there. There's been a lot of work over the last, I would say, 5 to 8 years on the discrete alignment. There's still more to be done there. But this idea of both aligning and segmenting at the same time is still very open. So let's discuss that a little bit. So continuous alignment is this, remember, alignment is about finding the connections. We're not yet at interaction. Interaction needs a response. Connection, we're really trying to find what is co-occurring. That's an easy type of connection. Just some terms we bring back. And when we think of these continuous alignment, there's definitely at least 2 families of it. One where the alignment itself is we keep everything in continuous space and we're aligning, and we often use the term of warping, of transporting, and in these cases, while the other solution is to take a continuous and transform it in discrete, and then your life is everything is tokens. I know tokens. I know how to handle tokens. I put them in my transformer and I'm happy. So definitely discretization is another approach to that. So I will give you a few examples. I'm not trying to be exhaustive, but just giving you example in these two. And for continuous warping, when you're aligning, you have two videos, maybe two videos of two different people doing the same action, maybe kicking a ball, or maybe the same person, but from two different modalities, and you want to align them. And there's one algorithm. It's like impossible to talk about this alignment without talking about this one algorithm. I will try it. What is this one algorithm to align, to warp two signal videos? Signal processing. Okay, dynamic time warping is probably the simplest, but still quite interesting, and gives you a nice starting point. And there's extension of that with CCA and a lot of others. But dynamic time warping is the idea that you have two signals, and you're not really looking specifically at co-occurrence in this case, but at alignment and at how well or how easy it will be to transform one signal into the other. That's kind of the way to see it, how the closest match I can. And the main problem with the warping is, and that's a good example is in speech, you may have the same word, but spoken much faster or much slower. So really one of the hardest part of the warping of the alignment here is that events can be a little bit slower or faster. And a lot of those signal processing are really about just handling this, oh, the action was done a little bit faster or slower. Now, if the action is completely like my one action I've always seen on the right hand, and suddenly I do it on the left hand, that's a very hard for these algorithms. They're not, I mean, you could imagine extension that could handle symmetry like this, but these are really designed where you have an example and then you're doing it much faster or much slower. Maybe reverse, but even that, for the typical dynamic time warping, reverse is hard because then suddenly you're mapping the first with the last. A lot of these algorithms suppose that sub-events happen with the same order. Maybe some sub-event has not happened, you skip, that can be handled. But the idea that you're completely doing a different order of the sub-events, these algorithms, but the by default version of that, have a hard time. So just to share with you what it can do really well, but also where the challenges in the future are. So in this case, I have two words that were spoken, slightly one faster than the other. And this could be, I don't know, the average amplitude or one of the Mel frequency values that I'm plotting over time. Or it could be one joint angle on my leg because I'm looking at two kicking. So I have these values. For now, you could say each of these values are one dimension, but in reality, they can handle multi-dimension. So each of them could be all the joints. So that will be one observation, and you have one observation that's multi-dimensional, and you do over time. I'm just plotting one dimension here. And so the basic idea is that you only have one choice to make in this. And the choice to make is what are the indices that are mapping to each other. That's the only decision you can make. So you have indices from 1 to 6 for the first signal and 1 to 8 to the other signal. And your goal is to find pairs. You know how we did alignment discrete? Discrete alignment is all about aligned pairs of data. Here, you're going to try to discover those pairs. So here, the loss will be over this vector. That's always the length of the longest of the two. You always pick the longest of the two, and the other ones will need to be stretched. That's a clear, for this kind of task, you're saying the shorter one will need to be extended. I just don't know where to expand it. That's the basic idea, is that I know that the shorter needs to be expanded to longest. So I will have it to both of them length of 8, but now I need to find what are the indices. In a sense, for one of them, it's clear, it's 1 to 8, the longest one. But for the others, you will need to adjust. So that's the challenge here. So let's go ahead and see how do you do this in practice with dynamic time warping. Is the idea that you will, in a sense, explore all possibility. You have 8 and you have 6, and there is all this possibility of going, and as I told you, there's a few assumptions I made. I made the assumption that it's monotonicity, which is mostly the sub-events are going to be in the same order. They're just going to be smaller or longer. There's continuity. So in this basic version of dynamic time warping, there's continuity, which means none of the sub-event will disappear. There's extension that will handle that, but there you suppose that all the sub-events have been, so if I speak a word, that all the phonemes will be there, that you're not just going to swallow some, like in the East Coast. If you look at the spelling of Worcester, which really spelled like Worcester, but just a bunch of like poof things disappear. So yeah, so that's an example of a gap. And then there's just to help to make it manageable, some boundary that you would put there. So really the dynamic programming is going to kind of try all of them. You start from a known place, 1, 1. You start there and you end to the last 6, 8. So that end and the start is there, but then you have all of the in between. And to do that, you're going to look at the similarity of each of these links. Did I have it there? No. So there is a similarity function that needs to be defined. And as the similarity function I'm optimizing, here is a very simple similarity function of just differentiating like just the distance between the two. Now there's a nice extension of that will do a CCA or a correlation on top. There's a lot of very interesting extension. You can make all of it non-linear, like that you make it, so you always use this, it sounds fancy, like a kernel. What's a kernel? Oh my God, that's super fancy. Kernel is a distance function. It's a distance function. That's what a kernel is. A kernel is about measuring the distance between 2 points. What's beautiful with kernels is that they're very efficient to measure very complex distance function. You can, in fact, project it in a very complex space, but in fact, compute their distance very efficiently. So when you hear about like nonlinear kernel, or in fact, some of them even project in infinite space, like RBF. So here I can replace this with any distance function I want. It could be a distance function that implies that I'm learning multiple layer neural network and then measure the cosine similarity between the embedding. So all of the above, like there's a lot of extension of this. So, but the basic idea is to efficiently do through linear programming, dynamic programming, to explore all of the possibility. And I'm going to reuse that. In fact, you remember last Tuesday, we talked about optimal transport. It is also using a kind of linear programming as well, of trying all possible permutation. But in the case of the global alignment, you had discrete elements, but you didn't have this monotonicity aspect where, and that's a good practice for Thursday morning. Monotonicity aspect is that the sequential information, you did not have that. And so in the linear programming we were doing, we allowed the first to be aligned with the last, if you remember in this case. Okay, but there are a lot of other ways to do it. I'm going to show another one that I like quite a bit as another way to align two videos or two modalities. In this case, it's two videos. So you could imagine that you have a bunch of videos of people doing an action, but they're all doing them at different speed or different and what I like of it is this is doing, in fact, what is this lecture is about alignment and representation learning. So it's trying to say, hey, I know there's a problem in the alignment in my data. My data is not synchronized in a sense. It's asynchronized. And so I know that there's going to be a problem with synchrony, but I'm trying to learn a representation. And in this exact paper, the representation was unimodal. So it's trying to learn the same visual representation. How do I take a video and embed, or how do I take frames and embed them? And I want to do recognition, maybe recognizing action in this case. But what I will imply is that there's nothing stopping you from having two different modalities, modality A and modality B, where both of them are signals. The difference is you're not going to use the same encoder. In this case, they were learning the same encoder. The encoders have tied weights, okay? So because they know they have the same modality, but in a multimodal case, you will have it different. But the fun part is how do you do the alignment? That's the cool part of that paper. How can you define a loss function that enforces this alignment between and the general idea is which frame is closest to me and which frame they think is the closest. So you expect a symmetry between their similarity. That takes a little bit of time to understand. Is the general idea is that if you want to have consistency in the cycle, what it means is that if I believe that you are the closest frame to me, I have all these frames here. If I believe, I am going to say for this frame, if I believe that you are the closest, if there is a consistency, that frame, if I look from this perspective, I should be also the closest. There is in this algorithm an assumption that alignment is symmetric. If this element believes that I'm the closest, I should also believe that I am the closest to them. And if there is a difference, then we want to use it as a loss term. This is an error. So what it means is, and I'm going to show the algorithm in more details in a second, is that here it's a perfect match. I think that you're the closest, and if I go from the other, they think that they're the closest. But here, maybe I think that this is the closest to me, but for them, they think the closest. There's an inconsistency in the cycle. I'm going to call this an error. I want this to be the closest possible. So I want the embedding of this frame to be closer to that frame than this frame to this frame. Okay, I want the embedding to be as close. The cycle, I'm going to tweak. The only thing I can change is my encoders. That's the only thing I can change are the encoders. So I'm going to change the way I embed each modality in a way that I keep as much similarity as possible. We're going to talk later. There's a cool multimodal extension that came, in fact, from this class. That was a project in this class where people are doing it between modalities. And the general idea is if I say a word, I don't know, happy, and I translate, that was a slightly different approach. And here, translate it in another modality, like the smile happy, like a visual representation of happy. There should be a consistency that gesture also match again to the modality. There should be a two-way similarity between the spoken words and the visual representation, and back to the visual representation to the language. Here in this case, as I mentioned, it's a unimodal case. So let me go and see this algorithm in a little bit more detail. So I have my encoder. In this case, it's the same encoder for each, the source and the target. And it's a two-step thing. The first step is a typical finding the attention or the closest to mine. So I have this original frame, let's say the frame at I, and I'm going to look at the similarity between I and all the other frames here. And then I'm going to just compute a distance. And then I'm going to weight all of them. So here, what I do, which is different, is instead of doing a hard selection, a hard attention, they do a soft attention. They say, hey, from this frame, like from all of them, what are like the prototypical frame that's the closest to me? Because the real frame may be just between two frames. I'm right there. So this is the prototypical frame that looks the closest to me. And then they take that prototypical frame that looked the closest to me and look back from all of these, I just copied them here, and look back at which one looks the closest to that prototypical frame. And I look at the peak of that, and the distance, that little distance, is my loss. So I have a frame. I look at, in the other modality, all the closest, and I have an attention, soft attention, and I take a weighted average of them, and that looks at like the prototypical closest in that modality. And now I look back and I say, hey, from that frame, what are the closest? And I look at the similarity function, and then I think in this case they were fitting a Gaussian to these to find the mu or the middle of it, and then you just have a nice distance from that. So you have consistency. If this is consistent, then you should always have no distance between those indices. That's the idea here. Yeah. You will end up doing that for all frames if it's your question. So for that frame, I will have a loss term, which is the distance between that frame, which is repeated here, and the closest match from the other modality. And then you will do that for all frames in U. And I forgot the algorithm, but I think they go and do it the other way around. They will do from V and do the same inverse thing. What was it? No, in this case, you suppose that one frame, it could match with many, but I'm going to find one prototypical of that. So in this sense, yes, there is. But when you match back, I'm really wanting, like, if really there's a plateau, like I'm as good as this, like because they're all good, then the loss is not going to be as strong. It's more of a flat Gaussian. I think the variance of the Gaussian is good. Like if it's a very peaky Gaussian here, like very peaky here, that's not including me, I'm like, I don't fit. But if it's a broad Gaussian, okay, I'm not going to penalize at it as much. So sorry. So to answer your question, sorry, I kind of wrongly answered at first. It will handle the many frames in a sense, many continuous frame by fitting the Gaussian to it and just having a very large variance, and then I will not penalize it as much. But if it's very spiky, and it's not you, then you will hurt. Yeah, good question. Yeah, that's the penalty term. So this is the continuous. There's a lot of interesting work. I just gave you 2 examples. And then there's discretization. So because a lot of the previous approach, suppose I had like either a list of discrete objects or something else, but there are many examples where either you have a signal and then it's unclear where or how to segment it. Even videos, like it's not always clear when the start and an end of an action is happening. And there's definitely a lot of interesting work, like for example, in medical imaging, I'm going to give you one example primarily, in fact, two examples of it. The first one is if you have a signal and you want to segment it, and you have supervised data. What supervised data is that you already have someone annotated the sub events, the segments. You've already done that. Then it's a much easier problem. It's still really painful to annotate it. You also need to have an annotation scheme of what the sub-events are. But for some fields, like in speech, like there's a lot of work on like phonemes and understanding that. So in this case, there's nice data set that can take the spectrogram and annotate to phonemes. But you have the same issue that we had earlier about speaking faster and slower. So in this case, they will need to handle that. So that approach, I will say, is the mix between discretization and continuous alignment, because you still need to handle that same issue of faster and slower. So, oh yeah, 30 minutes. So the approach for this is that because you can speak faster and slower, the same many audio frames, it's a many-to-one mapping. And so there are many algorithms to try to handle that. Sometime now they're just putting everything in a transformer and hope for the best. But there's some nice and interesting algorithms that were there. And I would say up to like maybe 2 years ago, this one was quite popular. Now we'll see it a little bit less, but I just want to give it as an example, which mostly the idea is that you already have this classifier that you train. You already train a classifier to predict these phonemes, but at test time, you're going to need to be able to handle that misalignment. So for every audio frame, you're going to have a prediction. For each phonemes, you have a prediction. That's kind of your logic. And you often add one for silence, no phoneme, that often added. And then the interesting part is a little bit like the dynamic programming in a sense, is going to be like finding the path in this, all these logics, all these scores that you have for the different labels, and trying to find which one is more likely to happen. And then what they did is added domain knowledge to it, where the most probable sequence, there's some expectation that if you have a phoneme, the next one is likely to be repeated. So there's a little bit of domain knowledge that were encoded in that algorithm to make it very efficient. And at the end of the day, you get this nice list of all the probable sequences on this. The one I like, and if I remember correctly, one of the author is also named Hubert. So that's a nice also for him. I'm still waiting for an algorithm called Louis-Philippe. So a little bit harder. Although I do have a store of clothing in India, so that's the first start. So, and I am wearing a Louis-Philippe shirt, so yeah, I love it. So anyway, hidden unit BERT is, and we'll talk about BERT hopefully today or the latest on Tuesday. But the idea is that I have speech, but now let's suppose I don't have labels. And then what is the number one algorithm you should think of if I have unsupervised data and I'm trying to find a way of grouping it? Clustering, k-means, like, and they all have fancy name. I love that name still, hidden unit BERT. But at the end of the day, it's just clustering plus transformer. With a smart little addition to that. But the basic idea is still the basic idea of clustering. And so I have all of these audio frames, and you can decide a hyperparameter how to, and then I will look at this and I will cluster And there's different version of this algorithm. You could imagine you do it offline completely. So all my audio frame, and I have k maybe equal to, I don't know, number of phonemes I think that language has, or bigger, or somewhere around that. It's a hyperparameter. And then the nice thing from all these clusters is that I will try to predict again these cluster IDs. And what it means is, if because the expectation is within an audio that there will be repetition. There will be repetition of the same clusters will be repeated. And the same intuition, as we will see in a second, is that knowledge about the previous samples hopefully tells me what's likely to be in my sample, what my observation. And so, and there, I know I've not discussed how magically I do this, but let's suppose I have this nice algorithm that will learn a representation for each of these audio frame. The idea, the same as we will see in a second for BERT, is that I will predict, I will hide. You remember the distributional hypothesis that we had in language, that the context can predict the word, the meaning can be approximated by its context. That's the same hypothesis they have here. They say the context is likely to be able to predict the masked word. It's just the only difference here is, instead of a word or a token, my token is just an ID that I got from the different clustering. It's a really nice. Now there's extension to make it audio-visual. The simple one would be to just concatenate audio and visual, and then just simply do the clustering. Or you can do more fancy way of aligning first the audio and the visual, and then do the clustering. Then a lot of the building concept I talked about earlier could come together. So, what is this beautiful transformer? And let's talk about, we call it contextualized representation. We sometimes call them aligned representation. These days, the landmark algorithm for it is transformer. But really what it is what are those algorithms that can do both alignment and representation learning at the same time? That is the key to the next part that I will talk about. So, and one I will discuss now is contextualized representation for sequences as a starting point. So in a lot of the work we've done up to now for representation for last week, we're looking at multimodal representation for two elements, one from each modalities. Now we'll embrace the fact that each modality has a structure. Language has this nice sequential structure. Videos will have something similar to that sequential structure. So the idea here is I want to learn a representation for each word, but I want to take into consideration that that word came as part of a sentence. And so the meaning of that word will be influenced by the words around it. And I picked this example because it's quite obvious. I do not like it. The like is definitely being affected directly. In fact, this have probably an effect on both, but definitely on the like. So the not like has an effect. So the meaning of like here, if I do it by itself, should be quite different from the one that is part of the sentence. I'm going to use this as my running example as we run through the, but how could I do it? We have the Elmo way. You remember, that's the very long, short-lived best paper word. But that one was doing bidirectional LSTM as a way of contextualizing. They were the one also bringing this masking idea that was very key later on for BERT, the masking idea. So that was a key aspect of it. Another way to do it is, in fact, the problem with this is that it's a sequential. And the reason in a second we're going to talk about transformer and all this is that they have this main advantage that CNN has also, is that they easy to parallelize. Here, to be able to embed this token, I need to have done all the previous token. So in this case, all token needs to be done sequentially. That reduces performance. So the other way is, when you think about it, the other way to do it is the CNN way to do, where you have these templates. And in this case, you could have a convolution that is ran temporally on this. And people have tried, there's something called temporal convolutional network, which are they're a 1D CNN that is then nicely slided over time with different kernels. So that's another approach. It can be parallelized, but long-range dependencies are not handled as well, because you do have those kernels, and those kernels are usually, I don't know, 5, 10, 15, like usually odd numbers, but still, you're not going to have those 201. Then you're kind of against this idea of local transformation, which is the landmark of CNN. So finally, the self-attention is really taking the previous concept we saw of attention. Attention, if you remember, is I forgot the father and the grandfather that I talked about. Gating is the idea that my parameters are dynamically computed. It's not just learned during training, but dynamically based on the observation. That parameter is always that weight, that attention weight. Now, if we call it an attention, is always gonna be changing. So if I have a different input, I have a different attention weight. And so attention weight, one of the main thing is that you're normalizing these score, these weights, and that's one of the, because you're attending by normalizing, you usually have a peak or it could be flat. So there, the idea of a self-attention is that every token or every sample is going to be attending to all of the other token, and I'm going to show it in a second. But the nice thing is that every token being connected, or every word being connected to every word, long-range dependency will be possible. And then we still have the advantage of the dynamic weights. Okay, so I know most of you, I definitely did it in PyTorch, so you're like, oh, I already know transformers, but I found that at least some of the intuitions are lost when you're just doing it in PyTorch in a few lines. So I will go step by step to really understand what it does, because I want you to understand, because there's no point in me doing the multimodal if you don't understand what this algorithm does, because it's not a magic, it's not magic. It does things really well, but it doesn't do everything perfectly. So we'll have to do that. So what the goal is that I want to learn a representation, and I already got a representation. That's the first key. The transformers and self-attention models are not about creating something from nothing. They need an initial representation. Now, the extreme version is to start with random, completely randomized. But no, you need some initial representation. If it was completely random, then these will not work. So you need to have some initial representation for each of those tokens or each of those observations. The really beautiful aspect of it is that it will find if there is any extra information in the other token that could be useful for your current representation. That's the key insight of transformers, is like, is there any information in the other token that may be useful for me? That's the key aspect of it. So internally, this model, let me do it for only one of them. I have this original representation. Now, it could be just a one-hot encoding, Or it could be that I've done, I don't know, word to vec, like a simple word embedding first. But a lot of times the first layer of these could be just a one-hot encoding of all the tokens for as a starting point. The aspect here is that there will be an algorithm, and I will tell you in a second how magically I get those numbers. But before I tell you how magically I get this, I'm going to tell you the second part, which is for this token, I magically, I just told you that the CNN, they're not magic. Okay. I smartly, no, interestingly, I managed to find how relevant this token is to itself. That's not as impressive. But the next one is how this token is relevant to this first token. That's the attention. How relevant this token is. How much it is relevant. How much this other token is relevant. How much this other token is relevant. And how much this other token is relevant. Now the transformer does a second thing that's really cool. It's not just that this token is relevant, but what part of that token is relevant is also changed. So it's not just a copy of that, but what part of that token is relevant to my first token? What part of that is going to be relevant to my token is also. And so what do I get as an output of that self-attention module is this list as long as the number of tokens observation. And there you do have how relevant it is and what part of the original token is relevant. And then it's a weighted average after that. So I multiply these. So how relevant it is by what part of it was relevant. And then I just sum it to it. So the self-attention, and you do this for this token, for this word, but you also do it the second time. In fact, it's done all in parallel. That's a nice thing. Is for this one, I also have the what is relevant, how relevant it is, but the decision of how useful this token is, this word is for all the others, is the same one. Okay, you don't recompute a different version of this. That would be a nice extension, but then it makes the parallel aspect of it a little bit harder. So the how useful I could be to all the others is decided once, but you have a different weight that says how important the word I is, or how relevant the word I is to do. That's this number. How relevant the word not is to the word do is this number. And then you do the same idea. You multiply, and then you add. So this is now what's really interesting there. This is now this what I had here multiplied by all of them. So I kind of multiply each of them, and I just sum it. There's one thing I didn't put in this slide. It got a little bit hard to do, but the one key aspect of the transformer is that, in fact, this is going to be added to the original one. It's a residual connection. What it means, it was getting a little bit hard to put, is that X is going to be here. And really, I should call this almost a delta H or delta X. It's like, so, and the residual, it took me a while even myself to completely understand it, but it's a very important thing, because this H is in fact the delta X. What it means is, what is it in all of the other words that can help me, that should change me? This H that is here is in fact a change over X. How can X be changed by any of the others? And that's important because that makes the task a little bit more manageable. It's no more the usual, in a sense, complete masking that I'm doing here. In a sense, I'm not trying, at this point at least, I'm not trying to completely recreate the X. That's not my goal. I'm not trying to make them, I may add all the way to the end, but here I'm not trying to I'm trying to find something that could be added to my current representation, and something that will be useful in all the other words that could change mine. And I will do that for every word like this. I kind of summarize it. So I have a vector here of how relevant this word is, this word, and then this word. That's all the relevance multiplied by this, added. This delta X then will be added to X. And then I get my new representation, my contextualized representation. So now how do I do this? That's the inside here we're going to do. How do I get those vectors? That's the main key aspect here. So the idea here is I want to know if this word, so the easy thing is just, I could just transform this with a linear transformation or nonlinear transformation. But the important part is here. I want to know which other word may be relevant to me. And the idea is mostly to knock on everyone's door and say, hey, I don't know how to ask, what would be a question to that? What would be a good prompt? And these days, everything's about prompt. So yeah, what is the right prompt to say, are you useful? Do you have any knowledge that's useful for me? And the idea is twofold. Each word will kind of say, hey, that's me, and I have this information available, kind of. And then every other word will then say, hey, is there a nice match? Is there something that's useful in that word? So there is a query. The query is saying, hey, that's me. That's me as a word, and I'm looking for a good match. And then I'm going to look at all of the other words, their keys. And so the key, we'll get to the value in a second. The key is the interesting thing, is that I'm going to compare my query to all of the keys. And that's the beauty of the self-attention here, is that I'm going to take every word, embed them in a new space, where they're exploring or they're showing what they have available in a sense. And then I have a query that's going to see if there's something I'm looking for. And then compatibility between these two spaces, like the key and the query, will really tell me if there is a match. So the word not, for example, is going to be one that says, hey, that embedding will be such a way that it will be like any verb that has a possibility of having its meaning change. I'm gonna, and not will be probably put in a space where any verb that has a possibility of being changed its meaning by not will be very close to it. So it is these, what I really want is be sure that query and not, that key, are very close to each other, because they're extremely relevant. The not and the like are very useful. They really can change the meaning. And so the algorithm, through gradient descent, the typical way of optimizing, will have changed these weights, these encoders, in such a way to be sure that if two words are likely to interact with each other, likely to have an effect on each other, then their query and their key are close to each other. That's the whole thing of the transformer, that the main power that it has is this, is say if two tokens are likely to interact with each other, and I will say transformer are, when we say they're contextualizing, it's a mix between connection and interaction, but there's definitely possibility of interaction happening in a transformer. And in a sense, you could imagine that the key and the query are a little bit about finding if two things are connected. And then the interaction will be, in this case, in a somewhat simpler interaction, will be about the adding the effect of the other. So by multiplying this and adding it to the original. But the interaction is, in this case, a little bit more of an additive in this case, because you're adding extra knowledge from the others. You keep adding new knowledge. Now, because there's often nonlinearity, that interaction can start being nonlinear. But if it was just one layer like this with nothing else on top, then this will be a nice way to do additive, in a sense, interaction added to it nicely. But the key and the query are there to find if there's a connection or if there's a link, if there's a relationship, something useful between them. So the algorithm will go ahead and find, for that query, try all different keys and say, hey, is there anything compatible? And that's the way these attention weights are going to be computed, by simply comparing that query with all of the keys. And then the similarity function has been decided when they created it to be very efficient by simply do a dot product, which dot product we know is a little bit similar to the cosine similarity of two angles, just to see if two embeddings are similar. Now, there's extension. People have tried more fancy version of that. It turned out that this is almost as good and definitely a lot more efficient and to compute. So the key aspect is you have the query, you have the keys, and then you repeat the same for the next word. So the word I do, and then I do, is it related with the I? Probably not as useful. But definitely when I get the do and a not, probably there, that value here is going to be high. That attention is going to be high. And the same way, and I say this is going to be high once the transformer is trained. We want this value to be high. During training of the transformer, that's going to be the challenge of the transformer, to change these weights in such a way that that query and that key are compatible to each other, so the attention. So the gradient, the loss, whichever loss we decided, will be done in such a way that when you propagate your gradient, that and you realize there was an error in your loss, that the only thing it can change, and that's the beauty of these algorithms, it's a little bit like convolutional neural network. The only thing it can change is those weights. And one thing also why transformers are good, the same with convolutional neural network, is that the weights here and the weights here and the weights here, they're all tied. What it means is the way I embed this word is using the same matrix as I embed this word, and same as I embed this word, same as I embed this word. So it's tied. And so number of parameters are very efficient. It's also very challenging. It would have been much easier if I can embed certain word a certain way and other words another way, because but in reality, because that input embedding is different, then once I multiply it, it's not that all of the keys are exactly the same. No, all of the keys are different because the input to that WK is different. So, but the transformation, the linear transformation I apply is the same for all input words. It's the same linear transformation I will do for all of them. So that's the only thing the transformer can do. The only handle or anything, parameters you can change are those weights, how you're going to embed a word so it is a good key, a good identifier of its other token it can have an influence on. So do not, I really want that key to be close to that query, and otherwise I'm going to have a high loss because I will not have changed correctly the meaning of the word do, and I will not have changed there. And so because of that, I will have done a mistake in my classification. So I will say, hey, you made a mistake, and I believe that these two should have been close to each other in a sense. Yeah, they are different. Yes, exactly. Oh, sorry, that's a typo. Okay, sorry for that. Good. I just wanted to be sure. Yeah. Only one person. Correct. Yeah. WV. Yeah. I just want to. So it's WV. So all of them will be a different embedding. So that mostly the intuition is that representation. If you remember, also the goal of this is kind of a delta X, because if you remember, I'm going to sum them to give that H, but I'm going to do a residual connection with the original X. So that if I could not just copy this over, because then I will be adding all of these to my embedding. That didn't make sense. So here, that embedding here is really transforming this embedding into a delta X, like a difference that could be useful for other words. Yeah. So that's what this embedding is going to do. Yeah. Was there some question? This is the most important. If we spend 2 lectures on this, it's good, because after that, it's just a bunch of architecture, engineering, and all this. But that's the core of it. So one question, and then the intuition, at least the way I see it, is that after I go through this one layer of transformer, I still want a representation that's close to what I had originally, but now I want it to be contextualized by the others, but I don't want it to be completely new value. And that's why the residual connection is that I put it here, and then I just add these two, and that becomes a new representation. So did I? So I'm thinking about doing the change for next year. I could have called this, I don't know if it's delta X1, but this one is a representation of taking the word I and projecting it in a space. Probably, I don't know if the magnitude, in my mind at least, the magnitude will be smaller of things, because it's mostly, hey, how can I influence other words? That's what this is. And so the not could say, hey, the not could be, the not in itself may have that representation, but the way it influences others may be in only one dimension, very strongly, not really influence the other words in only one of the dimensions. So that X3 here will be mostly, I don't know, 0 and 1, and because that's the way we establish that dimension changes from positive to negative meanings. So this embedding is about making it in a way that's useful for the other words. And then, as you were hinting, then I'm adding all of them together, weighted by the attention. And then I add it back to my original word. So yeah, so the delta is there in this case. Yeah. So there's quite a few answers to your question. Good question. Right now I'm purely unimodal. So let me answer the unimodal case, because even in the unimodal case there's something interesting, which is which I will show in a few more slides, but I can at least think about it. Is that every word could have multiple meaning. That's one thing, but also 2 words may have more than one way to interact with each other. Like there could be more than one way that things could interact with each other. So what happened is often I said that there's only one WK, like one way to embed the key and one way to embed the query. But in fact, the reality is that I'm going to do multiple, like a mixture of experts of that. I'm going to, in fact, usually train a typical transformer will have, I don't know, 5 to 10 of those replication. You're in fact training 5 or 10 of those transformer at the same time. And the idea is each of those, they call it multi-head. Someone woke up a morning, thought it was a good name. So multi-head is a mixture of experts. That's another one. But like, so is that you have more than one way that words could interact with each other. And the easy way to do is like allow the model to have more than one expert for each of these different ways that words could interact. Now, I didn't answer yet your answer about multimodal, but you could imagine that if you were to do a very simple multimodal version of that and just concatenating the language and audio in it, then multiple head could be one way to handle that differences. Now, I'm not suggesting that you do early concatenation of fusion. There's better way to do multimodal transformers. But if you were to use this architecture and simply concatenate, or there's also the idea of concatenating as a sequence. You have the tokens that are language and tokens that are audio. But the general idea that the way you contextualize words with each other is very different from how you contextualize audio with each other. And it's very different, as you hinted, how you contextualize audio with text. And the way to handle that is to have just different set of weights for each of them. And one way is multiple head, like a mixture, and we'll look at other alternative to that. Yeah, it's this vector here will be a dense vector representing it, not necessarily one hot. This may be one hot, but by the time it's here, it's rarely one hot. It's going to be a more dense representation. Yeah, the key is also a 1D vector. Sorry, so that's a good clarification. So here, this is a 1D vector, and this is a 1D vector, and then I'm just going to compare with the two vectors. In fact, it's kind of, but yeah, you're just going to multiply these and get one value. Repeat that question. Are you asking when when you say the key in the query, are you talking about the vector? Okay. So so if you originally have the first layer of a neural network of a transformer will usually be something like a one hot embedding, or it would be an initial non-contextualized way to embed words, like a word to vec. These will be maybe just randomly initialized. So at the beginning of the training, it's randomly initialized. So this vector here, maybe at the beginning, not really meaningful because it's just a key that's not really looking. But because I have a loss and a task, it will realize that certain certain query needs to be certain key. And because of that, it's going to change the W and the WQ and the K. And then these will, over many iterations of optimization, will start being closer and closer, these two vectors that are relevant to my task. So did I answer the question? Okay. Yeah. So yeah, I'm 100% sure someone has done it. And in fact, I'm quite sure that researchers at Google, when they put the residual connection, did empirically test it. From our own experiment, it does also, but not as extensive as other maybe people have done. But if you don't, you solve two things. There's one is the intuition that I gave you that now you're bringing together, you're not reinventing the wheel. Like you're not trying to recreate this at every step. So you're just trying to add. That's the one intuition. If you were to do without a residual connection, I would probably want that WK different from the others or something, because your own WK should not be embedded the same way as the other WK, because at the end of the day, I probably want that embedding to be very similar to my previous. So there will be a little bit of concern. The other reason is how do we call it? But a vanishing gradient is the residual connection had already been shown with ResNet and others to also help with the gradient, because in fact, by having a skip connection, a residual connection, you also have the gradient that can directly go to the next one. So it does help also with the gradient. So definitely, if you are going to have more than 2 or 3 layers, you're probably going to need also that residual connection for that other reason as well. Yes. Okay. Good. This is the most important, and so by a large margin, because if you don't understand that part of what really it does and what it does not do, like really at the end of the day, is transformers are a beautiful contextualization machine. That's what they do. And that's why when you think of fusion using transformers, it's a very different way than some other approaches that we've seen in week 3, because there's a lot of ways we found that like we explicitly either multiply or some like interaction. Like here, it's about additively adding new knowledge or new context that's useful for the embedding. Yeah, I think I'm going to give the annoying answer, which is hyperparameter. You optimize that hyperparameter, and there are some modalities that it's a little bit intuitive, like words, how many different meanings a word could do, or like there's a little bit, but at the end of the day, it has been kind of over the years knowledge that has been accumulated of what the range should be on this. Here in this case, the way we're going to do multimodal fusion is not by taking advantage of the heads. We're going to do it in another way. Right now, most of the transformer we'll use, even in the multimodal case, will be primarily about contextualizing each unimodal representation, each modality. So that makes the problem a little bit easier. But still, that's a good question. Unfortunately, I'm not aware of good theoretical grounds on how to select that hyperparameter, unfortunately. So, so this is transformer, and that figure of transformer for me, although it's really like hard to, but it's a lot more intuitive that then you're gonna see the original transformer that I don't know, let's not call it ugly, but like non-intuitive. It's intuitive at the higher level, but if you want to really understand the internal mechanics of it, of what's happening, you need to go look under the hood. And I think it's important to look and understand how under the hood it is working, because that's the key aspect, is this part, how the key and the queries are interacting with each other, how the value, why is that value, now it got fixed suddenly, how the value is there, the value, why did I not just copy paste that? And we talk with the residual, because it's the residual, is probably one of the big reasons, is that it doesn't make sense to just copy it. And what is it that the model can really do? This is just about finding similarity between tokens, and that's really the key aspect, the query and the key there. So that's the transformer, and then everything after that is a lot easier. It's just a bunch of nice, interesting addition to that. So, but the only parameters that you have in the transformers are the query, the key, and the values. And this is the only these are matrices we talked earlier. This is a matrix of size, whatever. This is the size and whatever the whatever this should be. So it's a decision that has been made. So they don't need to be the same length. So it could be like 400, and this could be decided to be only 200. Now, this has to be the same size. So this has to be symmetric. That one would have to be symmetric. Now, in practice, I believe they end up being the same length, but the key and the query don't have, in theory, to be the same size because they're going to end up being just a number. So these will not need to be. They may be in practice just to make things simpler. But that one needs to be a square because that needs to be the same length because it's going to be added there. Okay. So I'm just going to show one or two things after, just because we talk about what if there are multiple meaning or multiple ways that the words could interact with each other, and that's the multiple head. So multiple head, what it means is that you just have more than, so one head, you have 3 matrices, and that's the only thing that the whole model can change. Even if you have 200 tokens input, it doesn't change that. Now, suddenly, if you have multiple heads, you multiply by the number of heads. It's a mixture of expert. That's what it is. It's just adding. I believe it's added. You could multiply, I suppose, but I believe they're just. Yeah, no, I think they're added. I'm quite sure they're added because then that H is gonna then be, I believe. Okay, no, I didn't put it, but that H is gonna have the skip connection. So I'm quite sure it will be a linear projection. Oh, it's a linear projection, so it's kind of added to each other. I will probably stop here, but the nice thing that we just a little. This one is but a nice. I will tell you the problem. I will not tell you the solution, and you probably know at least at a high level the solution. But the problem is this: is that up to now there's literally nothing that tells me the position of tokens, and I will say this is, in my belief, we're not completely we don't have yet the strongest theoretical foundation to that question. We've have empirically things that work well for that solution, but by default, this transformer, if I take these tokens and I run them through these matrix, I will get the exact same values here. Okay, because there's literally nothing telling them the ordering. Okay, so the do not, like the do, will be the same as this. So H2 here will be the same as H5 here. That is, there's just nothing that would change that by default. And that's why they had to add something else. The reason it's really cool is that it does long-range dependency. Every word is connected with every word. The price they had to pay for that is now they lost that nice recurrence that they had in the previous one. And so they will need to do that, and they will need to add a position embedding to that. We'll talk a little bit more next week on Tuesday. Good luck with your first project assignment, and see you on Tuesday next week. Thank you.